In the previous video, we looked at the mean value theorem. In this one, we're going to try and prove it. So when you think about the mean value theorem, zoom your brain into this part here. What this part is saying is that the average gradient here. So this here represents the average gradient. So zoom your brain into this part. This part here represents the average gradient. And hang on, this part here represents the average gradient. So it's like you trying to break this down here, because it's like you trying to start at f of a and somehow climb to f of b, where you have to keep your gradient below the average gradient. Here, if you keep your gradient always below the average gradient, you will never reach f of b. In order for you to reach f of b here, then this gradient must be above the average gradient. So when you think about the mean value theorem, think about this part here. Okay, you could try and break it down by thinking of it like this. Look, my gradient here is going downhill, so the gradient must be negative. If it's negative, then it must be lower than the average gradient. Yeah, it's true up to this stage here, but if you look right from the start here, then your gradient here must be above the average gradient. My point is that when you think about the mean value theorem in your head, try and think about this part here, the average gradient here. This is your average gradient here. If you start at f of a, you're never going to be able to reach f of b if your gradient is always less than the average gradient. You're never going to reach it. The only way you would reach it, well, think of it like this. Okay, so in order for us, in this video, we're going to try and prove this. But in order for us to prove this, we need to know about Rolle's theorem, which I've explained in the past. But this here is a formal theorem. It is the proper way of stating Rolle's theorem. So Rolle's theorem is that if f of a equals f of b, if f of a equals f of b here, then somewhere in between the gradient must be 0. So you could do something like this here, somewhere in between. No matter how you draw it, somewhere in between the gradient will be 0. If you have something like this here, you see somewhere in between the gradient must be 0. There must exist one point, one C somewhere in between A and B where the gradient will be 0. This well, I've explained this several times in the past. Okay, so now we're going to try and prove this. So we are going to try and prove this here. Okay, so remember Rolle's theorem. We're going to need it later. So our aim here is to get to this stage here. I'm just going to give you an overview of this. It doesn't matter if you don't understand it. So the way we are going to try to get to this stage here is to do this. Draw a straight line that connects f of a to f of b. Okay, so we're going to come up with an equation for this straight line here, and then we are we're going to come up with an equation for this straight line, and then we're going to create a new function. Let's say anything here. We're going to create a new function where this function here will be f of x. Remember, f of x is this purple line here, f of x, and this here. Well, let's call it g of x here. The equation of a straight line here is g of x. We're going to define h of x as being f of x take away g of x. So what this h of x means is that if you look at this is f of x. And let's draw it. What h of x means is f of x here, which is this point here, take away g of x, which is the straight line here. Don't forget the straight line g of x. So h of x represents this gap in the middle here. This gap in the middle here. Okay. So hang on. So we're going to come up with an equation for a straight line, and then we're going to define h of x here as being f of x. So get the original function. And then we're going to take away the straight line. So h of x represents the gap in between here. H of x represents a gap. Well, if if you think of h of x as being the gap, if you look at the gap here, it's 0 here, and then it increases, and then the gap here gets smaller, and then it will get to 0. So when you plot a graph of h of x, it will look something like this. It will have a 0 here, because look, the gap is 0 here and the gap is 0 here, and then h of x will look like this. If you draw a graph of h of x, it will look something like this. And then we can use Rolle's theorem. We can apply Rolle's theorem here, because somewhere in between, because this point here is 0, this is 0 here, so somewhere in between the gradient must be 0. So when we get to this stage here, we will apply Rolle's theorem. I will continue in the next video. It doesn't matter if you don't understand this, but this is it's just an overview. We're going to do it properly in the next video. Okay.